Okay, welcome back. Last time we looked at this business of Lagrange interpolation. Now what I want to do this time is sort of give another example of the basic idea that went into the solution of the interpolation problem. Okay. So let me just call this the 0-1 idea. So in various contexts in which it appears, it goes under so you will see terms like duality or orthogonality and so on mentioned. So these are all words which will sort of appear whenever this idea is used in various places in mathematics. Now let us just call it the 0-1 idea for now, and we will look at an example of this. So what is the 0-1 idea? What do I mean by that? In order to solve the interpolation problem, you were given d plus 1 points, and we solved it by first doing the following. We found polynomials which were 0 everywhere else except at a single point where it was a 1, okay, and the final answer was more or less obtained by combining these various polynomials. Now let us do a similar thing in a different context. Now for this example, it will require a little bit of recall of what vectors meant and what vectors are in 3 dimensions. So I won't really go into all of the entire theory of vectors, just recall the basic things that I need. So here's the typical picture I have. So this is what you call R3. R stands for the real numbers. R3 is just 3-dimensional space. So I have 3 dimensions, and what is a vector? So what's a point in R3? A point typically is given by 3 coordinates x, y and z. So I have a point and the position vector of that point. So by the position vector I just mean, well, I join the origin to that point, so let us call the origin as O, and the position vector of the point A is just, well, we say it's more or less this ray which points from the origin to the point A. So the position vector, so A is the point and its position vector, if you wish, is usually denoted OA. It is the ray from the origin to that point. Okay, so now here's what I want to do. Okay, so maybe we'll just give an example of this. So if a point is let's say A is, let's say, the point 2, 1, minus 4, then the position vector of A is usually written as follows in vector notation. We say it's 2 times I cap plus j cap minus 4 k cap. This is the conventional way of writing this, where what are I, j and k? They just refer to the unit vectors along the x, y and the z directions, right. So this is the usual notation. So I have I, which is along the x, j which is the unit vector along the y, and k which is the unit vector along the z directions. Now there are natural operations that one can perform on vectors. So there are 2 of them called dot and cross product. So for now let us just recall what the dot product of vectors meant, of 2 vectors. Well, it's given by the following thing. Let's again just do it by example, just recall what dot product means. So suppose I have a vector, say 2i, let's even take the one that we wrote down, plus j minus 4k. That's a vector. So dot product, sometimes also called the scalar product, dot with, let's say, 3i plus 5j plus 7k. Here's another vector. The dot product of these 2 vectors is defined to just be, you sort of do the following. You multiply the x components together, that's 2 times 3 plus the y components are 1 and 5, 1 times 5, plus the z components are minus 4 times 7. And so the whatever that is, so that's 6 plus 5, 11 minus 28, so that's going to be minus 17. Okay, so that's the definition of the dot product, and recall again that the dot product contains some geometrical information regarding the angles and lengths of vectors. Okay, so here are 2 vectors. The dot product sort of encodes some information about the angle between them and what their lengths are and so on. Now what I want to pose is a problem of the following kind. So, I want to take 3 points in R3. So, I have well, here I have a point A, I want 2 more points B and C. So, what you are given are 3 points in R3. So, given 3 points in R3, and what else? Well, so I might want some restrictions. I want them to be sufficiently independent in some sense, but let us not worry too much about these things right now. So, given 3 points in R3 and 3 real numbers and 3 real numbers. Okay, so what shall we call them? A, B, C, just arbitrary real numbers. So, here is the problem: given 3 points in R3 and given 3 real numbers A, B and C, find a point D in R3 such that it is satisfying the following conditions. The position vector of D has prescribed dot products with these 3 other position vectors. So, I have 3 position vectors OA, OB and OC. I want OD to have dot product A with OA, dot product B with OB and dot product C with OC. Okay, so, again it is sort of like the polynomial condition. I have three given vectors and I want the dot product to be certain values at those 3 points. Okay. So, let us see what would the 0 1 idea refer to in this context. It is the following: before we solve the general problem in the earlier case, we sort of found those special polynomials, right. So, similarly here let us solve a special version of this problem. So, let us solve the case when A is 1 and B and C are both 0. So, let us do the following: let us solve this problem when, well, A equals 1, B equals 0, C equals 0. In other words, I want to find a point D such that the vector, the position vector of D has dot product 1 with OA and has dot product 0 with the other 2 fellows. Okay. So, that is the first thing. So, let us call the solution as the point D that you get. Let us call the solution I do not know, instead of D let us call it D1. So, similarly let us solve another problem. Let us find a point D whose dot product is 1 with OB and 0 with the other 2 vectors. Okay. So, suppose we can solve this problem, call the solution as D2, and we solve the third problem, which is dot product 0 with the first 2 vectors and 1 with the third vector, and call that solution as D3. Okay. So, instead of solving the general problem, we solve 3 simpler problems. Okay. We find D1, D2 and D3 whose dot products are zeros and ones, right. That is sort of what the 0 1 idea means. Now, suppose we could do this, we still do not know how to do this, but assuming we could do this, then here is how we solve the general problem. The solution to the general problem by which I mean the original problem with the 3 given real numbers A, B and C. How do you solve the original problem if you know these 3 solutions is the following. You just take the solution to the general problem is given by, so you define the position vector OD as you have 3 position vectors OD1, OD2 and OD3. You just take a linear combination, you say it is A times this plus B times that Okay. So, I have these 3 points D1, D2, D3, and here is the linear combination A, B and C, where those are the given 3 numbers. This linear combination we claim is going to be a solution to the general problem. Okay. So, let us check this, let us check that this is in fact true. So, what do we need this point D to satisfy? It needs to have prescribed dot products with OA, OB and OC. So, let us compute what is OD dot product with OA. Let us see whether this answer is exactly A. So, observe what is the property of D1. Okay. So, D1 I said is a solution to the problem when A equals 1, B equals 0, C equals 0. Okay. So, what does this mean? By saying that the solution is D1, it means that D1 has the following property: the position vector OD1 has dot product 1 with OA and 0 with the other two fellows. That is what D1 does. So, let us compute this. So, OD dot OA would be OD1 dot, so it is A times OD1 dot OA, B times OD2 dot OA and C times OD3 dot OA. And observe that sort of again by doing the same thing for D2 and D3, that this would be a 1, this dot product is a 1, while the other two dot products are in fact zeros. So, it is plus B times 0 plus a C times 0. So, the answer is exactly A. Okay. So, similarly if you worked out what the dot product of OD with OB was, then only the second term would give you a 1, whereas the first and the third terms would give you 0. And similarly for the third guy, you would only get a 1 in the third term and zeros in the first two terms. Okay. So, essentially if you could solve 3 simpler problems, you can solve the original problem by just taking a linear combination. Okay. And observe, this is exactly what we did for interpolation as well, because there we solved, we found those polynomials PI's, and then we just had to take a linear combination of them, and that solved the more general original problem. Okay. So, the last step remains is really the following: can we solve this problem? Is this any easier to solve than the original? Okay. So, it often happens that these simpler problems are in fact simpler, meaning they can actually be solved by some easier method, like in the case of the Lagrange interpolation. Finding those PI's is actually very simple, because it is 0 at D points and non-zero at only one point. So, because it was 0 at those D points, we were able to use the fact that it must have each of them as a factor, like each of those x minus xi's would be a factor of the polynomial P and so on. So, that greatly simplified the calculation. We were able to quickly figure out what the PI, the form the PI must have. Now, here is another instance where a similar thing happens. It is actually easier to solve these problems. So, let us just do it by example, since I am sort of really only trying to demonstrate what the broad idea is in this case. So, here is my example. I will take my point to be, I need 3 points. So, I will take 4, 1, 2, I will take a point P which is 1, 2, 1, point C which is 1, 1, 1. So, let us say those are the 3 things that are given, and let me see how would I solve. I will just demonstrate how to solve the first problem. How do we find D1? Okay. So, suppose I want to find a point D1 such that, let me just call it D, such that the dot product of OD with OA, OB and OC is 1, 0 and 0. Okay, I am trying to find a point D which is, well, has inner product, has dot product 1 with OA and 0 with the other two vectors. Now, just like in the polynomial case, the fellows with whom it has value 0 sort of give you a lot of starting, they form a very nice starting point. From that you can get quite a lot of information about the polynomial. So, observe here that the fact that it is dot product 0 is, well, again this requires a little bit of recalling what a dot product means, being dot product 0 means that this is actually perpendicular to this vector. Okay. So, dot products really mean the following, that OD is therefore orthogonal to or perpendicular to the vector OB, and it is perpendicular to the vector OC. Okay. So, this is a property of the dot product, that it is really, if it is 0, it means the angle is 90 degrees between those two vectors. And so, this vector OD that we are looking for is, it is a vector which is perpendicular to both OB and OC. Okay. So, if I have two vectors, let us say OB and OC, and I am looking for a vector which is perpendicular to both of them, then this vector is given by, well, the easiest way to get it is by what is called the cross product of these vectors. So, observe OD is perpendicular to both OB and OC means OD in fact lies along the cross product of these vectors. Okay. So, I will just briefly recall what cross product, the rule, at least what is called the right hand rule for the cross product. You sort of look at OB and OC, and where does it point along, you sort of go from OB to OC with one's right hand, and the thumb points in the direction of the cross product. So, that just gives you an idea of what the direction of the cross product is. So, it means that OD is in fact parallel to the cross product. So, in other words, it must be, you take OB cross with OC is a cross product of vectors, and you could possibly, it could be some multiple of this, let us call it some multiple m, some real number m times the cross product. Okay. So, it points out or could point in if your multiple m is negative, but at least what this has done is it has quickly given us a starting point for the form of OD. Okay. So, all we need to do is figure out what the cross product of these vectors is. So, let us do that. So, there is again the standard formula for a cross product. So, in terms of a determinant, so I am not going too much into this right now. So, hopefully this is familiar, if not it is something that just a small ingredient which you should be able to refresh quickly. You sort of write a determinant I, j, k, and let us see what are the vectors. You write 1 2 1, write 1 1 1, then sort of, this is a formal way of remembering what the cross product looks like. You sort of say it is I times 2 minus 1 and so on. So, I am not getting into the rule itself, this is not too important for what I am going to do. Let me just write down the answer itself, it is I minus k. If I compute the cross product of OB and OC using whatever rule you are familiar with, the answer turns out to be I cap minus k cap. So, I know therefore that OD is some multiple of that vector. Now, which multiple is given by the other condition that I know on OD. I know that OD is supposed to have dot product 1 with OA, right. So, that determines that multiple for me. So, observe OD is m times I minus k. So, I will compute its dot product with OA, and well, what is the answer? Let us do this. OA is 4 1 2, right. So, I have m times I minus k dot product with 4 1 2. So, this gives me, so the dot product rule that I just wrote out, it is 4 minus 2, so that is 2. So, I get 2m, and this is supposed to be a 1, right. So, this tells me that m is half. So, in other words, this d that you are looking for is just half of I minus k. Okay. So, that tells you what the solution is. So, the point D is so that's the solution finally. The position vector is half of I minus k, means that the point is just half 0 minus half, right. So, here is a way of solving the 0 1 problem. You just sort of take the cross product of the remaining two vectors and then to figure out which multiple of the cross product it must be, you sort of see the dot product with the remaining vector, and that will tell you what the scaling in front needs to be. Okay. So this is just an instance of the 0 1 idea of trying to find something which is 0 on everybody except on one fellow on which it is a 1.